All right, guys, before we get started, are there any questions on the homework? Questions over any of the homework assignments? So far we have had 3 assignments, 7-1, which was our inverse and direct variation. 7-3-1 was simplifying and multiplying rational expressions. And then Friday, 7-3-2 was our dividing rational expressions. So we've had the 3. So what we've done so far is multiplication, division, which leaves us with our last 2 operations, addition and subtraction. Addition and subtraction. Now, addition and subtraction can be nice and not nice all at the same time. Because it will be nice, because if we add or subtract 2 rational expressions, we add or subtract 2 fractions, and the denominators are the same, we add or subtract the numerators, whichever operation we're using. So in that case, it can be nice. So if we're looking at 5/9 plus 16/9, since the denominators are the same, we add the numerators. So we'd have 23/9. If it can reduce, we need to reduce it. 23/9 doesn't reduce. So that is our final answer. So we're looking at some of these here. The first one we're going to look at is 7 over 4x plus 3 over 4x. Yes. Since the denominators are the same, we can add the numerators. So 7 plus 3 is 10 over 4x. Questions on this so far? Now, we can say that this is the final answer as long as there's nothing in common on top and bottom. Is there something in common with our 10 and 4x? 2, a common factor of 2. So we have to reduce it. If I reduce 10 by 2, we get 5. If I reduce 4x by 2, we get 2x. So 7 over 4x plus 3 over 4x gives us 5 over 2x. And that's our final answer. Now again, you don't have to list restrictions on the homework, especially for these here. But again, I'm going to bring it up so that we do have it in our mind. As our restrictions are whatever is going to make the denominator be 0. In this case, whatever is going to make 4x be 0. Now, there's 2 different ways we can go about solving this. One is we divide both sides by 4, telling us that if x is 0, the denominator would be 0, so x cannot be 0. The other is that we could have just said 4 times x equals 0, x has to be 0. In that, our 0 product property. If we multiply 2 or more things together that equals 0, one of them has to be 0. So we're multiplying 4 and x. 4 can't be 0. The only thing that can be 0 is x, so x has to be 0, yeah. Because that's 4 times x. 2 things multiply together equals 0. The only thing that can be 0 is x, so x has to be 0. So all it's telling us that here, x cannot be 0. Questions on this here? All right, let's look at the next one. X over x plus 6 minus 5 over x plus 6. The denominators are the same. They're both x plus 6. So we can subtract our numerators. So on top, we'd have 2x minus 5. Now, we do need to be careful with subtraction, especially where the 5 is that term, because if there's more than one term there, so like x minus 6, that negative is going to have to be distributed to every term. Here, there's only one term, so we can just say 2x minus 5. We've applied it to every term in the second one. 2x and 5, are they like terms? No. So we can't actually subtract them. Is there anything in common between 2x and 5? No. Is there anything in common on top and bottom? So there is the x, yes, and it's very tempting to want to cancel the x and x out. But the plus on bottom, that x plus 6, is a single term. We can't just simplify it down. They're stuck together. The same on top, 2x minus 5, those are stuck together as a single term. If there was a multiplication of x or something being multiplied on top and bottom, we had two terms being multiplied, yes, we could simplify. Simplifying with multiplication is nice. We can simplify it out. Addition and subtraction, not so much. They're stuck together. So that is it. That's as simplified as it gets. Questions on this here? We'll look at the next one, 8 over 12x minus 5 over 12x. The denominators are both 12x. Since the denominators are the same, we can subtract the numerators. Three over 12x. So yes, 5 minus 8 gives us 3. 3 and our 12x do have a common factor of 3. So if we take a 3 out of 12x, we do have 4x. And if we take the 3 out of 3, what do we have left? 1. And if the 1 is left on top, we have to put it. If the numerator is reduced to 1, reduces out, everything reduces, we do have to write the 1. If the denominator, the bottom of the fraction, reduces to 1, we don't have to write it. Division of 1, dividing by 1 is understood. Having 1 on top, we have to list. Questions on any of this here? All right, let's look at the next one. 2 over 3x squared plus 1 over 3x squared. Since the denominators are the same, they're both 3x squared, we can have the numerators. Giving us 3 over 3x squared, which reduces to 1 over x squared. And again, the restrictions on this is going to be x cannot be 0 in actually both cases. Questions on any of this so far? (4x over x minus 2 minus x over x minus 2). Since the denominators are the same, we can add or subtract, in this case, subtract the numerators. So here we're going to have 4x minus x. Let's look this up here. Now 4x minus x is what? 3x over. Now again, this is as simplified as it gets, because that x minus 2 is a single term. It's stuck together. We can't just take the x away. No way we can factor the top and bottom as simplified as it gets. That's all we can do with it there. We're ready for the next one. Now the denominators are the same. They're both x squared plus 1. So that means we can add the numerators. We can add the 2x squared and 2. Almost. Are they like terms? No. So one of them has the x squared, the other doesn't. But they do have something in common. They do have the 2. So we factor the 2 out just to make sure there's nothing in common. Because whenever we simplify, we want to factor the top and bottom as far as we can get it, and then see if there's anything in common. like we did in the first part of 7.3. Because if there's something in common, we need to reduce it out. Now this here does reduce, because what's in common on top and bottom? The x squared plus 1, the whole term on top and bottom is the same. And that leaves us with so this one here, I want to look at the restrictions because they're kind of interesting. So what can't be 0 in this case is x squared plus 1. Because if x squared plus 1 is 0, that's our restriction. It would cause a division of 0. So to solve this, the first thing we would do is subtract 1 from both sides, telling us that x squared would be equal to negative 1. At this point here, we can take the square root of both sides. Well, the square root and square would cancel, telling us x is equal to plus or minus square root of negative 1, which is I. So, according to this, if x is positive I or negative I, it would cause the denominator to be 0. But is I a real number? No. So let's look at it graphically. So this here is the graph of x squared plus 1. Does it cross the x-axis? No, it doesn't cross the x-axis at all, does it? So is there any value of x that will make this be 0? No. So what that means for us here, that the restrictions, well, there aren't any. There are no restrictions for this, because there is no value of x that would make the denominator be 0. Because most of these, it feels like that there's always going to be a restriction, some value that will make the denominator be 0. No, sometimes there's not. There doesn't have to be. And that's why I said this one's interesting, because this actually doesn't have restrictions. There is no value of x that will make that denominator be 0. Questions on this here? All right. As I said, adding and subtraction can be nice and not so nice. The not so nice is when the denominators are not the same. Yes. All right. So if the denominators are not the same, we're going to have to get them to be the same. So that's one of the things that makes adding and subtracting fractions not as nice, because if the denominators aren't the same, we got to get them to be the same. And for the most part, especially what you all encountered up to so far would be, say, 3/4 plus 7/9. If we're having to add or subtract these, well, all I have to do is grab a calculator, do 3/4 plus 7/9, it'll tell me the answer. Unfortunately, with these rational expressions, again, both calculators will not use, it won't help us with variables. We're going to have to actually make them be the same. Because the calculators can calculate it, but it's going to stick whatever number was last put in for that variable, and it's actually not telling us the answer we want. Because here, what we're trying to find is the least common denominator. Or the least common multiple of 4 and 9. We're trying to find the first number that I can make 4 and 9 both be. Least common multiple is going to go up. It's either going to be 9 or greater. And it works out that the first number that both 4 and 9 are is 36. Because 9 times 4 is 36. 36. 9 times 3 is 27. Now we can add them together. Telling us that we have 55 over 36. Because again, for us to be able to add or subtract fractions where the denominators aren't the same, we're going to have to get the denominators to be the same. And that's finding this least common multiple or least common denominator. And the only real difference between the two is least common denominator is talking about the bottoms of the fractions, the denominators. Least common multiple, we're just talking about the numbers themselves. So for this here, the least common denominator is 36. The least common multiple for 4 and 9 is 36. It is essentially the same thing. It's just all in the context of what we're using. So if we're talking about making two fractions be the same, we're looking for the least common denominator. If we're just looking for what's going to make the two numbers be the same, first number that we can turn both of them into, least common multiple. Same concept, just it's how it's applied. So before we jump straight into doing these here with fractions, we're going to work a little bit with going back over least common multiple. So we want to find the first number I can turn 8, 14, and 16 into. Looking for the first number, we can make all three of these be the same. And again, we're going to go up. It's going to be easier to go up, increase the number than it is to decrease, especially with fractions. Because if we're trying to decrease, that means I'm dividing a fraction by a fraction. I'd rather multiply. So there are different methods for this. The first one is skip counting. That means I'm just going to list every multiple of 8 out. So 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96, 104, 112, 120. All right, hopefully that's enough. Then we're going to repeat the process with 14. 14, 28, 42, 56. Okay. We do have a number in common at 56. So that could be the least common multiple, the first number we can turn both of them into. I'm going to go out a little bit further because 72. No, not 72. Because 14, 0, 70, 84, 98, 112. So we also have 112. And there's other numbers where we will eventually hit that repeat. Those, anything higher than whatever the smallest one is a common multiple. It's just not the least common multiple, the smallest one of the group. So between 8 and 14, 56 would be the least common multiple, the smallest one we can turn both of them into. 112 would be then the common multiple, would be another one we have. Now we're going to do this again with 16. 16, 32, 48, 64. Well, this went clear past 56. So 56 is not the least common multiple because it's not across all three. 16, that'd give us 80. 96. 112. So the least common multiple is 112. So this method works, and it will work every time. But the issue I find with this here is when we start getting bigger and bigger numbers, because it's going to take longer and longer to get through the factors, especially the smaller numbers, to get to whichever number we end up getting. Because if it ended up being that the least common multiple was 1,064, it's going to take us a while to get there by 8, if that is indeed it. So again, the bigger the number gets, the longer it takes to get there. So let's look at the second method. Second method is going to deal with factors, or prime factors. Well, the easiest way I've found to find prime factors is factor trees. So I always start with the smallest prime numbers and go up from there. And our first prime number is 2. Is 2 a factor of 8? And it's 2 times 4. Well, 4 is 2 times 2. 2, 2, 2. We have all prime factors, yes? So we can simplify this as 2 to the third power. We have 2 times itself 3 times, 2 to the third. That is the prime factorization of 8. 14. Well, hey, it's even, so 2 is still a factor. So we can do our first tree, 2 times 7. 7's prime, yes? That's it. Prime factorization of 14, just 2 times 7. Let's look at 16. 2 times 8. Weight is 2 times 4. Everett, if you'll grab the door. Yeah. So 16 is 2 times 8. 8, 2 times 4. 4. 2 times 2. Well, how many 2's do we have? 4. 4. 1, 2, 3, 4. Okay. Questions on how we did the factor trees of these here? Now, to find the least common multiple, I want the greatest, I'm going to look at all 3, and whichever of these numbers has the greatest amount of a given factor, we're going to take that many. So let's look at 2's. How many factors of 2 did 8 have? 3. Okay, it has 3. 14 has 1, and 16 has, so which one has the most? 16 at. So for the least common multiple, I need 4 2's. So I need whichever one has the most, and I need that number of them. So since 16 has 4, we're going to take 4. And it's not so much that 8 has 3 or 14 has 1. They do have that amount, but we're looking for which one has the most because we're trying to get them to be the same. It's easier to multiply, add factors in than it is to take them away, and we don't want to repeat. Because if I wanted to turn 2 to the third into 2 to the fourth, all I've got to do is multiply it by 1, 2. I have 4 of them now, yes? 2 by itself, well, we can multiply it by 2 to the third, multiply by 2 3 more times. Those 2 are now all the same. We look for which one has the most, and that's what's going to be taken for the least common multiple. Well, the only other factor that we have is 7. 14 has 1 of them. 8 has 0. 16 has 0. So how many 7's do we need? 1. And it also tells us what we would need to multiply these by to get them to be the same. So 8, 2 to the third. We're missing a 2 and a 7. We multiply it by those, we get 112. 14, we're missing a 2 to the third. We multiply it, we get our 112. 16 does have our 2's, it's just missing a 7. Multiply it by that 7, we get it to be the same. Questions on this here? Do we want to do the skip counting for this here? Or do we want to do the factors, our factor tree? Factors, factor tree. 9, 12, 15. Well, 9 is kind of nice because the factors of 9 are 3 and 3. for us would be 3 squared. We have 2 of them. 12. 4 and 3, so we can say 3 times 4. And 4 is 2 times 2. So the prime factorization of 12, we'd have 2 squared times 3. 2 times 2 times 3. 15 would be 3 times 5. Both of those are prime numbers. So that is completely factored. So let's look at each of our factors first. So 2. 12 has 2 of them. 9 has 0. And 15 has 0. So how many 2's do we need for the least common multiple? 2. Let's look at 3's. 9 has 2 3's. 12 has, 15 has. So how many 3's do we need? 2. Because whichever one had the most, since 9 had 2, we need 2. 5's. 15 is the only one that has a 5, and it shows up once, so we need it once. 2 squared times 3 squared times 5. It would indeed be 180. So the first number we can turn 9, 12, and 15 into is 180. Questions on this here? All right. So we kind of get the feeling for how this works, yes? All right. Let's throw variables in. Now before we start figuring out all the factors and doing that there, what's going to be helpful for us here is to actually factor these. Because 4x squared minus 16 and 6x squared minus 24x plus 24, neither one of these are factored. So we're going to factor them. So with our 4x squared minus 16, is there a greatest common factor between these two terms? 4. Because if I factor out of 4x squared, we're left with x squared. If I factor 4 out of 16, we're left with 4. X squared minus 4 is nice. It is a difference of perfect squares. So what times itself is x squared? And x. What times itself is 4? And our signs would be plus and minus. Okay. So 4x squared minus 16 factors of 4 times x plus 2 times x minus 2. All right, let's look at the other one. 6x squared minus 24x plus 24. There is a greatest common factor of 6. All right. So when we factor the 6 out, we're left with x squared minus 4x plus 4. Third term's positive, so the signs are the same and match the sign of the middle term. So negative and negative. What's the factors of x squared? X and x. Now factors of 4 are 1 and 4, or which one do we want to use? 2 and 2. And x minus 2 times x minus 2 are indeed the correct factors. Okay. Least common multiple. So we're looking for the first thing we can turn both of these into. Now, with the last two, when we looked at each set of factors, we picked whichever one had the most and included it in our least common multiple. I'm going to start with x minus 2. Our 4x squared minus 16 has how many factors of x minus 2? 1. It just has one set, yes? Our other one has how many? So how many times will I include it? Twice. So we can say x minus 2 times x minus 2, or x minus 2 squared. Since it showed up twice, we need it twice. Let's look at x plus 2. Shows up once here. It doesn't show up any in the other, so we need it. Now we just need to figure out what the least common multiple between 4 and 6 is. And it is indeed 12. Because luckily, even if we do skip counting for this here, 4, 4, 8, 12, 16, 6, 12, they're both kind of nice. Or if we look at 4, 4 is 2 times 2, 12. 6, 2 times 3, so its least common multiple. 4, we have 2 twice, compared to 1. 3 is only listened once. 2 squared times 3 is 12. So our least common multiple, the first thing we can turn both of these into is 12 times x plus 2 times x minus 2 times x minus 2. Is the first expression we can turn both of these into. Questions on this here? We'll do this tomorrow.